This presentation is based on the first chapter of the ebook To Infinity and Beyond by Dr. Kent A. Besse. The notion of infinity has fascinated philosophers, scientists, and mathematicians for millennia. Its enigmatic nature seems to thwart all attempts to unlock its secrets. Scriptural allusions to the infinite evoke a similar sense of mystery. Few have been as intrigued by the concept of infinity, or as tenacious in trying to understand it, as the German mathematician Georg Cantor. Between 1874 and 1884, Cantor published numerous papers that illuminated some of the shadowy regions of the infinite. He discovered a remarkable realm where half of a pie is as large as the whole. Infinity comes in different sizes, and miracles become mathematically plausible. Cantor's journey to infinity began as he considered the task of determining whether two collections of things, called sets, contain the same number of objects. This, of course, could be accomplished by simply counting the objects in each set and comparing the results. If the sets are large enough, however, one may not finish counting within a lifetime, many lifetimes, or ever. Another approach, which lies at the core of Cantor's reasoning, is to find a way, if possible, of pairing the objects in each set. For example, suppose we want to know whether the BYU Idaho auditorium will accommodate all individuals intent on attending a devotional address. Let P represent the set of people who would like to attend the devotional. Let S represent the set of available seats. Inviting all such individuals into the auditorium and asking them to take a seat will quickly reveal the relative sizes of the two sets P and S. If every seat is taken and no one is left standing, then the number of individuals is the same as the number of seats. In this case, we say the sets P and S have the same cardinality. If, after all the seats are taken, there are still people standing, then the number of individuals is more than the number of seats, in which case we say the cardinality of the set P is greater than the cardinality of the set S. Finally, if everyone is able to find a seat and there are still seats available, then we say the cardinality of the set P is less than the cardinality of the set S. Some might wonder how this simple exercise could possibly shed light on the concept of infinity. But consider this. Did we at any point need to know the actual number of individuals or seats when comparing the sizes of the sets P and S? No, we did not. The pairing of a person with an available seat circumvented the need to know how many seats there are or the number of attendees at the devotional. Through pairing, we can determine whether the cardinality of a set is less than, more than, or the same as the cardinality of another set without knowing the number of objects in either set. Armed with this technique, Cantor made discoveries that profoundly altered mathematicians' views of infinity. Applying the pairing procedure to truly large sets, such as the set of positive integers, he concluded that the set of positive even integers has the same number of numbers. This follows because a pairing can be made between all the numbers in both sets. In particular, by doubling each number in here, we get a number in here. So that 1 is paired with 2, 2 is paired with 4, 3 is paired with 6, 4 is paired with 8, and so on. In general, each positive integer n is paired with the even positive integer 2n. Therefore, the set of positive integers and the set of positive even integers have the same cardinality. It is possible to miss the significance of what we just did. We have shown that a part can be as large as the whole. In other words, half of a pie can be as large as the whole pie. Ordinary intuition proves inadequate in the realm of the infinite. Mathematics students soon discover this when they study infinite sets for the first time. As a point of discussion, consider the scripture, "And he that receiveth my Father receiveth my Father's kingdom. Therefore all that my Father hath shall be given unto him." Giving away all that one has is a sure road to penury. Consequently, some have argued that this scripture refers to the sharing of power. But receiving another's kingdom and being given all that the other has seem more tangible than the sharing of power alone. Suppose this scripture also refers to the sharing of tangible, though perhaps celestial, possessions. Can we still make sense of the scripture? I believe we can. Each year I assign my advanced students the following problem. Consider the set of positive integers. Let each positive integer represent a 1-ounce gold coin. Suppose all these coins are yours to share. By means of either a formula or a diagram, show that you can give an infinite number of these coins to an infinite number of people, while retaining an infinite number of coins for yourself. Faced with a challenging mathematical problem, a person would do well to tackle easier versions of the problem first. In the present context, a good place to start is to identify a way of sharing infinitely many of these coins with one other person, while retaining infinitely many coins for yourself. A simple solution is to give the other person the gold coins associated with the positive even integers, while retaining the coins that correspond to the positive odd integers. Next, you might try devising a procedure that assigns an infinite number of these coins to an arbitrary but finite number of people, while retaining infinitely many coins for yourself. Once you have accomplished this, you are just one step away from solving the original problem. Pictorially, the solution is elegant and accessible. Arrange the positive integers, which represent the 1-ounce gold coins, into an infinite diagram. You keep the gold coins associated with the positive integers in the first row. You give the next person the gold coins associated with the positive integers in the second row, and so forth. So indeed, it is possible for you to give an infinite number of these gold coins to an infinite number of people, while retaining an infinite number of coins for yourself. Said differently, a sufficiently wealthy person can share an equal portion of his or her wealth with many other people, while retaining the original amount of wealth. Cantor did not stop his investigation of infinity here. What he did next was so breathtaking that prominent mathematicians of his day refused to give him audience to justify his results. He demonstrated that not all infinite sets are of the same size, of the same cardinality, and that some infinite sets are tremendously larger than others. He proved, in other words, that there are different sizes of infinity. Many mathematicians at the time of Cantor dismissed his discovery of higher orders of infinity. But today, Cantor's work on infinite sets is considered one of the greatest achievements in the field of mathematics. Equally tantalizing is the relationship between 2 and 3 dimensions. Imagine, if you can, what it would be like living in a 2-dimensional world, where spatially there is only forward, backward, and left, right. There is no up-down movement. It just does not exist for you. Your world is restricted to a flat surface, such as a tabletop. You cannot jump up from off the table because in your world there is no up. Geometrically, you have a length and a width, but no height. For simplicity, suppose you are a circle with its interior as the inside of your body. Outside the circle is the world around you in this two-dimensional universe. Unknown to you, there is a larger three-dimensional world of which your world comprises two of the dimensions. Such individuals, living in 3 dimensions, would have full view of you and others on the tabletop, but could easily remain out of sight from everyone in your two-dimensional world. Yet inhabitants of 3 dimensions can choose to be seen, at least in part, by coming in contact with the tabletop. For example, imagine placing a glass, which is 3-dimensional, on the table. The bottom of the glass, being in contact with the tabletop, can be viewed by those living on the surface of the table. It would seem to have appeared out of nowhere and can disappear just as quickly by lifting the glass off the table. Perhaps more intriguing, suppose you, as a circle and its interior, become ill with cancer. You opt for surgery to remove a tumor. Removing the tumor in your two-dimensional world requires cutting through your circumference, the outer portion of the circle that encloses your interior body. This is the only way a doctor in your world could surgically get to the tumor. But suppose a benevolent, competent individual in the three-dimensional world wanted to help. The tumor is in full view and is easily accessible in 3 dimensions without needing to cut through you. Assistance could come from above as a 3-dimensional benefactor performs surgery from inside you, and the entire procedure would be hidden from the eyes of 2-dimensional observers. Analogously, the 4th dimension or higher would be an ideal place for spirits or heavenly beings. They would have an unobstructed view of our 3-dimensional world while remaining invisible to us. They could make contact with us and even change the course of events. Mathematicians are not perturbed by the notion of higher dimensional spaces. In fact, the 4th dimension, mathematically speaking, is quite prosaic. Cantor commonly worked with n-dimensional space, where n can be any positive integer. For example, in 53-dimensional space, instead of having just forward, backward, left, right, and up, down, you have 50 additional choices of directions. Talk about freedom! But 53 dimensions would seem restrictive compared to still higher dimensional spaces. Freest of all, one may surmise, is an infinite dimensional space where you have an infinite number of degrees of freedom when moving about, revealing worlds within worlds within worlds. The enchanting qualities and protean nature of infinity continue to captivate and stir the imagination. Cantor transformed the mathematical landscape by his inquiries into the infinite. He discovered a realm of paradox and poetry of a sort never before encountered, where human intuition has little authority. He demonstrated the value of a single, simple, right idea. Above all, he altered mathematicians' view of infinity as an interminable process, a verb, to an actual entity, a noun. It was as though he had been inspired by imagery evoked in William Blake's poem, Auguries of Innocence, to hold infinity in the palm of your hand.